Hey, so welcome back to numerical analysis. So last time we talked about a lot of historical examples in numerical analysis. Some things for like, excuse me, some things like finding square roots. We had Heron's formula for that. I talked about computing logarithms for log tables, and yeah, that was fun. And what else did we do? I recorded those last two. I recorded that last video like 5 minutes ago. Now it suddenly is out of my head. Oh yeah, Archimedes and also Fermat. So yeah, that was a really long lecture, but just to get you an idea of what we're going to be talking about. But now we want to move into proper numerical analysis in sort of a modern context, and so I think the first few things I would like to talk about, and maybe it's out of order from other things, but it's sort of my comfort zone, is polynomial approximations. And so this is going to be talking about things like using Taylor series. We're going to be using interpolate. We're going to talk about interpolation, talk about the Weierstrass theorem and Bernstein approximations, and each of these is going to be their own lecture. But before we can talk about that, we need to have some sense of what it means to be close to what we're trying to compute, and this is going to apply to everything that we're going to talk about in the future. So we're going to take a couple lectures, and we're going to talk about things like metric spaces, and or not really metric spaces, and that's really more the metric space concept is more appropriate for advanced calculus analysis, intermediate analysis, depending on where you are, what it's called. Which is probably about the same level. You're probably taking this class. If you're in this class itself, then intermediate analysis or advanced calculus is probably on your horizon for taking it either concurrently or in the next semester. So so we're not going to talk about metric spaces, which involves a little bit of metric topology and things like that, open sets, closed sets, whatever. I'm saying things that you're not going to have to know. So don't panic if this all sounds crazy. But we do need to talk about metrics and what they are. So, and because you can't do a numerical analysis without knowing if you're close to something. And that's what metrics allow you to do. So, generally speaking, you've been dealing with metrics since geometry. If you take a look at 2 points in a plane, you can compute their distance by using making a triangle between them and using Pythagorean theorem, right? There are other ways to do it. So you can say take that triangle and you take this length squared plus this length squared, and then you add them together and you get the square root and you take square root, and that gives you a hypotenuse, and you say, haha, that's the distance between these 2 points. There's other metrics. One's called the taxicab metric, where basically you don't take square roots and you don't square, but basically you just take that one leg and then the other leg that are right angles to each other, you add them together, and that's your distance. And that's called the taxicab distance, mainly because if you're, say, in New York and you're driving on a grid, it doesn't matter if the actual geometric distance is, say, square root of 2 for like a 1-1 triangle. You're gonna every single time, or rather, yeah, 1-1 square root of 2, right? Yeah, square root of 2. Sorry, mental lapse there. But basically, if you're driving, you're going to have to go 1 and then 1, and so it's distance 2 no matter what you're doing. And so it gets called this taxicab distance. I think it's been called the New York distance. It doesn't matter. L1 distance, if you really want, is another way to think of it. But yeah, so that's another metric. And so those are metrics on the plane. There's all sorts of different metric spaces for all different sorts of problems. And so we're going to be concerned with mainly the Euclidean distance, which is one you get out of the Pythagorean theorem. And we're also going to be concerned with what's called the uniform metric on continuous functions. So we need to have, if we're going to be talking about getting close to functions and approximating functions, you can't talk about that without some sort of metric. And so you have what is called the uniform metric or the supremum norm on the space of continuous functions over, say, a closed interval. More generally, you would say over a compact interval, but again, I said that we're not talking about topology, so we'll just say closed interval, and we'll leave it at that. But basically what you know is that if you take two different functions that are continuous over a closed interval, we have the thing that we call the extreme value theorem, which says that over a closed interval, every continuous function takes a maximum value. Well, if we take two continuous functions, their difference is a continuous function. And if we take their absolute value, that is also a continuous function. And so then you can ask what is the largest value you can take on that closed interval where you have the difference of these two functions and then with an absolute value on it. And then whatever that maximum value is, you call that the distance between the functions. Another way to think about it is you can think about it as sort of what is the smallest envelope that you need to put around one function to get to another one. And so you can basically say that if you are within distance 0.1 of a function, say I'm not going to draw with my fingers, that makes no sense. But basically if you're 0.1 from a function, then you can take that function that you're trying to approximate and put a little, and expand it a little bit by, say 0.1, and you know your approximation lives within that 0.1 little tube all around that function. And so that's going to be really essential for what we're going to be talking about. I'm not sure if I'm going to include this in this lecture or not, but there's also this idea of a big O notation. Depending on how much time we have at the end of the class, I haven't actually recorded it yet, but that's going to be something I'm going to do. But basically we're going to talk about something called big O notation, which allows us to the idea would be to give us this sort of way of describing convergence and a comparison between two different quantities. So for polynomial approximation, one quantity that we might be talking about would be, say, the order of the polynomial. And so basically you want to have some sort of way of describing how fast you're going to be converging based on the order of the polynomial. And so but then if we talk about integrals, basically usually what we're going to be talking about with integration is we're going to have an area under the curve, and that we're going to be trying to compute. And we're going to be doing that with a lot of rectangles. But each of these rectangles has a width to it. And so then we think is if we use more and more rectangles and we make the width smaller, that ultimately we're going to have some sort of convergence based on that width going to 0. And so we'd like to be able to sort of dominate the error that we're going to be having by some other quantity h. And then a really convenient way of writing all this down is in big O notation, and that's really common in numerical analysis, and it also comes up a lot in computer science. It doesn't come up as much as you'd think in some engineering fields. I had somebody to laugh at me when I was telling them that we're using big O notation, and they thought it was like some awkward thing, but I don't know. It's a really common thing in mathematics. We have big O notation, we have little o notation, and we also have, I think, theta notation. And so we're going to talk about all of those at some point. So that's how they're going to happen in this lecture. It's going to happen next, but just give you a little preview of what's coming. And yeah, let's go ahead and get into it and talk about what a metric is. All right, and I'll see you on the other side.
Okay, so like I was saying in the lecture, we can't really talk about closeness or convergence or demonstrate that anything that we're even talking about is going to work unless we can actually demonstrate, unless we have some sort of definition of what it means to be close. So this necessitates the introducing a definition of metrics, and then also we're going to talk about sequences and series, and we're also going to talk a little bit about continuous functions. So this lecture might end up being longer than I expected. And I guess we'll see how everything goes. So generally what we're going to be talking about is we're going to be talking about metrics over a set, usually x, and although x, we usually denote by x, and x is frequently r or rn or something like that. So it's a vector, it's real. Something like that. But x could also be complex. It could be continuous functions, things like that. That isn't actually too uncommon. So we can say, or x is going to be, say, this collection of what we call continuous functions on an interval. So a to b to r. We'll get to that context later. But first, let's just talk about generic sets. So a metric, so we'll start off with a definition. And here, and we're going to say a metric, which is going to be denoted D from, basically that's mapping from x to x to, say, positive real numbers, is a function such that we have 1, the distance between x and y is the same as the distance from y to x, or d of xy is equal to dyx. We're going to say that the distance between x and x is 0. And by the way, we're saying that x and y are both coming from x, this set. Let's see, what else? In 3, we have that dxy is always greater than or equal to 0. And 4, and this is called the triangle inequality, if we also have for, say, x, y, z, and x, we have that dxz is going to be less than or equal to dxy plus dyz. Okay, and so this is a metric. So an example of a metric is Euclidean distance, and so this is going to be, say, we usually use d sub e if we actually use this notation. It's going to be xy is going to be the absolute value of x minus y, and so this is the typical sort of distance that you have in Euclidean space. Is a, so you're going to say this is a metric over R, or more generally, we see that dE of xy for x and y in Rn is equal to the square root of the sum from, say, I equals 1 to n of xi minus yi squared, right? And so that is the Euclidean distance. And we say that dE is the Euclidean distance on Rn, right? And we haven't defined continuous functions, but just thinking of continuous functions as coming from calculus is basically what we're going to say is that, let's see, so we're going to let C going from A to B to R be the collection of continuous functions on the interval A to B. So it could be polynomials, could be an exponential function, could be sinusoids, whatever. Then we define, then we know we have the extreme value theorem, which states that every continuous function f takes a maximum value on the closed interval AB. And so then we also know that the absolute value of a continuous function is continuous. So if f is continuous, then we know that the absolute value of f is continuous. And if f and g is continuous, then the absolute value of f minus g is continuous. Right? So what does that mean? So using these three ideas, then we know that the absolute value of f of t minus g of t takes a maximum value on AB, and we define a metric on the space of continuous functions from A to B to R. Often we'll just write CAB as the maximum. So we say that d of fg is equal to the maximum of t in AB of f of t minus g of t. So we know that since this is a continuous function, it takes a maximum value by the extreme value theorem. And so this quantity is well defined. So I sort of skipped ahead here. I mean, we haven't even defined what a continuous function is, but we just defined what a metric is. And we're already saying things like the extreme value theorem and all these other things. Really, at this point, I'm just trying to give you an idea of a couple of examples of metrics, and we will fill in as we go. But I just want to get. But the thing is that these two metrics, the Euclidean metric and the uniform metric or the supernorm metric, are really important. So this is the uniform metric or distance on CAB. And that is a closed bracket. Okay, good. Okay, so that gives you two examples of metrics. So let's go on and talk about some sequences, and then using metrics we can then talk about convergence, and then give you a proper definition of what a continuous function is. So so we're going to let x be a set. A sequence is a countable collection, is a countable and ordered collection of points say P1, P2, P3, etc. All within X. So if you want to get really formal about this, as we would say, a sequence is a mapping from the natural numbers to x. And so generally speaking, we would say 1 maps to P1, P2, P3, etc. But that just gets to be kind of convoluted. We can think of it just as what we usually do in Calculus 1, where basically we denote the sequence as say P curly brace Pn, where n goes from say 1 to infinity, or wherever we want to start. And so yeah, so that's the sequence. Now we say that a sequence Pn, where n equals 1 to infinity, which is contained in X, converges to a limit L, which is a member of X, if for all epsilon greater than 0, there exists an n in the natural numbers such that for all n bigger than n, we have that the distance between Pn and L is less than epsilon. So I should probably also say given a metric d on X, we say that a sequence converges to a limit L if for all epsilon bigger than 0, there exists an n such that for all n bigger than n, we get this, we're less than epsilon. What does that mean? Well, basically the whole idea is that if I were to write this horizontal line here as L, and we have a sequence of points, so here, basically we'd say, for instance, for here, if I want to get within, if I want to say that we're going to be within the threshold here, then it happens for all n bigger than this. But if I want it to converge, I need to be able to take this, these top two lines and shrink them down. So for instance, if I need to be able to find some n so that I stay within this window of L, then I would say maybe that happens after this point. And so basically we're saying as we shrink these different heights or distances, as we go forward, there's going to be some point that we're going to stay within that region altogether, so it sort of squeezes in towards L as we go to infinity. These are all sort of quick slapdash introductions to what would really be considered advanced calculus. But these are some ideas that we really just need for talking about distances and whatnot. So we'll keep going. Okay. So, some nice things about limits. I guess we'll write this as proposition. So we'll call this properties of limits. We're going to suppose that xn, pn and qn are inside of R, and we're going to be talking about the Euclidean distance. And so we'll say, so we have these sequences inside of R, and with the Euclidean metric. All right. And we're going to assume that Pn converges to L and Qn converges to M. Let's not say M. Let's just say K. Okay. So I guess first thing we should say is C for if C is in R, then C times Pn converges to C times L. We also have that the sequence Pn plus Qn converges to L plus K. And we can put a minus sign on there too, so plus or minus. 3. The limit of Pn times Qn converges to, let me just say, don't put braces there, Pn plus Qn converges to that. Pn times Qn converges to L times K. And 4, if K is not equal to 0, then Pn over Qn converges to L over K. And finally, the absolute value of Pn converges to the absolute value of L. Okay. Some of these are pretty trivial to show, but I guess I'll go ahead and do it. So I'm not going to demonstrate all of these. It would take too much time. This one is going to be pretty straightforward to do. And so I might as well show this one, and I can show this one. All right. This guy follows pretty quickly, just because the absolute value of x minus y bounds x, absolute value of x minus absolute value of y. And so I'll probably make this an exercise to demonstrate that, and then you can prove 5 here. Let's see. Okay, so let's go ahead and start off with the first one. Let's do this in green. So proof of, say, 2. So if you're actually taking advanced calculus, then that's something that this will help you with. This will help you prove some things in there. But yeah, let's go ahead and do it. So we're trying to show, so we want to show that Pn plus or minus Qn, but I'll just say plus Qn, putting the minus sign doesn't really change anything, converges to L plus K. All right, so we already know that Pn converges to L and Qn converges to K by hypothesis, so we're going to let epsilon be greater than 0, and we're going to suppose that n is in natural numbers and m is in the natural numbers, such that Pn minus L is less than, say, epsilon over 2, and Qn minus L, minus K is less than or equal to, or say less than epsilon over 2. Okay. So all I did is, I'm really doing this not just for epsilon, but I'm doing this for epsilon over 2, and you'll see why in a second. And so this is going to hold for all n bigger than n, and this is going to hold for all n bigger than m. And so I'm just going to take n tilde to be bigger than the max, or to be equal to the max of n comma m, right? So as long as you're bigger than n tilde, you're bigger than n and m. So, so we're going to let n be bigger than n tilde. Then what we're going to have Pn plus Qn minus L plus K is equal to, it's going to be Pn minus L plus Qn minus K. And using a triangle inequality, we get Pn minus L plus Qn minus K. And this is less than or equal to epsilon over 2 plus epsilon over 2. And this is equal to epsilon. Okay. So we just verified that. Not too bad. Let's go ahead and do the product. Well, I guess we can talk about this briefly. Let's see. So basically what I did is we know that Pn converges to L, and we know that Qn converges to K. And so we really just need to choose n that's going to be close enough to L and m, so that we're going to be close enough to K, that we're going to be within epsilon over 2. Why epsilon over 2? Because when we split this up into two different absolute values, we'd like to be able to express this as epsilon. Though I should emphasize, if we just did epsilon instead of epsilon over 2, we would have just gotten 2 epsilon at the end, and that would have been easy enough. And that would have been fine. Just as long as we can just keep making epsilon smaller and smaller, we can just pick an epsilon that would be underneath 2 epsilon, etc. We'd pick another epsilon that would end up making 2 epsilon into epsilon. Anyway, epsilon over 2 just keeps everything cleaner. Okay, so that was property 2, and let's do property 3. So proof of 3. Okay, let's see. So basically what we're going to have is we're trying to show, we want to show that PnQn converges to L times K. Okay, so let's go ahead and take a look this time and just see what we're going to need. So over here in just some scratch notes, let's do it. So if I take a look at PnQn minus L times K, that's not immediately something that it jumps out to me as like, you know, you split with a triangle inequality. So we're going to have to do some clever addition type stuff here. So I'm going to do some Pn times Qn, and then I'm going to add Qn times L. And then I'm going to subtract Qn times L. So I'm essentially adding 0. And this times minus Lk, because that's what's in there. So this is exactly the same. I haven't changed anything yet. And then I can rearrange this. So I can take a Qn times a Pn plus Pn minus L. And I also have plus L times Qn minus K. All right, and so that's fairly good. And so then what I would do is I would split this off as a Qn in absolute value times Pn minus L plus L in absolute value times Qn minus K. All right, so what are the quantities that we can make small? We can certainly make this small here, and we can certainly make this small here. We're going to have to use some other idea though, and this is a lemma that we can come back and show later, but I'm just going to write it down here. So lemma is that a convergent sequence is bounded. And that's fairly easy to show, and maybe we'll just make this as sort of a homework, but we don't want to do too much. But what we mean by bounded, it means that I can replace, that means that there exists an M in the reals. Let's not do M again, actually. Let's say there exists an R in the reals, such that Qn is going to be less than R. Okay, so we're going to make this assumption here, which you will prove in an exercise. Okay. But don't worry, we'll get away from this sort of more analysis type stuff when we get into actual numerical analysis. But first, we need to build some basic ideas. So now let's go back in here. So what we're going to do is we're going to let epsilon be greater than 0, and suppose that n and m are in n such that the absolute value of Pn minus L is going to be less than epsilon over R and over 2R, and that Qn minus K is going to be less than absolute value of L over 2, epsilon over 2 absolute value of L. Okay. Now, and this is going to be for all n bigger than n, it's going to be all n bigger than m. And then we're going to take n tilde to be bigger than the maximum of n comma m. Okay. So, so then for n bigger than n tilde, we have what? So we're going to start off with what I said before. We're going to have Pn minus Lk. And I told you before that we can then break this down into Qn times Pn minus L plus the absolute value of L times Qn minus K. And that's those equations on the right-hand side. Now, if Qn is bounded by R, then I have R times Pn minus L plus the absolute value of L times Qn minus K. All right. And now we know by how we selected n that what we're going to have now is it's going to be less than or equal to R of epsilon over 2R plus the absolute value of L times epsilon over 2 absolute value of L. And so these terms are going to cancel. It's going to leave epsilon over 2 plus epsilon over 2, and this is equal to epsilon. And so, therefore, we've demonstrated that this converges. So thus, Qn Pn times Qn converges to L times K. Okay. And I think for the interest of time, I'm going to leave this one as an exercise as well. Okay, so those would be good to get your feet wet as far as convergence goes. Okay, so quick notation. We say we write the limit as n goes to infinity of Pn is equal to L if Pn is a sequence converging to L. Okay, so what else can we do? Well, we can now talk about nice things like continuous functions. Now, continuous functions, this is more or less what you would experience studying Calculus 1. So given x and y, or say given sets x and y, with metrics dx and dy respectively, a function f mapping from x to y is continuous if for every convergent sequence, say Pn subset of x, the sequence f of Pn and y converges. Moreover, the limit of f of Pn should be equal to f of the limit as n goes to infinity of Pn. Okay. So that's pretty nice. So we can talk about examples of continuous functions. And the big one is polynomials. So let's see. So basically, the idea is that basically what we're going to have is that we know that, say, the function f going from the reals back to the reals, given as, say, f of x is equal to x, is continuous. So that's good. More than that, we also know the reason why we know it's continuous is that basically if, say, Pn converges, then f of Pn is equal to Pn converges. All right, pretty easy. Another one, f of x being equal to constant is continuous. And that's because constant sequences are continuous. All right, sorry, are convergent. Okay, not bad. And then after that, we have products. We have f of x equal x squared is convergent, is continuous. Sorry. And this is since f of Pn is equal to Pn squared. It's equal to Pn times Pn. So the product property of limits helps us. So the product property gives convergence when Pn converges. Okay. So good, and then higher powers similarly. So f of x equals xn. Similarly, we can say by induction. Okay, not bad. All right, now we know linear combinations work. So then linear combinations of continuous functions are continuous, and that just follows from the sum and the scaling property here. So very straightforward to show polynomials are continuous. Okay, so good. So what do we know then? All right, so how can we use this to our advantage? So I wanted to talk to you about Heron's formula. Now, I apologize for square roots. And I apologize for my handwriting going to crap. This is the second of 3 lectures written up today, and my hand seems to be giving out. But we'll get this done. All right, so let's talk about it. So Heron's formula for square roots. So we're going to prove that the numerical method that Heron came up with actually converges, and we're going to need something. Is called the arithmetical geometric formula or inequality. So AM GM inequality. This is really straightforward. Basically, what we know is that basically we have that a plus b over 2 is going to be always gets backwards. I think it's less than the square root of a times b, or it's the other way around. Well, let me check my notes. Something I always screw up. Nope, other way around. Yeah, all right. Yeah, I should have done that. So the arithmetical average, the arithmetical mean is bigger than the geometric mean. All right, and the proof is really straightforward. Okay, so this is actually pretty easy to show. We get 0 is less than a minus b squared, so the square of any real number is positive, and this is equal to a squared minus 2ab plus b squared. Now if we add 4ab on both sides, we get 4ab on the left is less than or equal to a squared plus 2ab plus b squared. Now I can write this on the right hand side as a plus b squared. Now I divide by 4 and I take square root, and so then that tells me that I get square root of a times b is less than or equal to, if a is equal to b, a plus b over 2, right? So done. Pretty straightforward. Okay, so now let's go ahead and talk about Heron's formula. I guess we should also mention one last thing about sequences and the real numbers, and this is the monotonic convergence theorem. Monotonic convergence. I don't know if that's really the proper name for it. That might confuse with something out of measure theory. But, just for our sake, a monotonic sequence theorem, I'd say that's probably a better name for it. Basically, if, say, Pn is a sequence in Rn, or sorry, a sequence in R, such that Pn plus 1 is less than Pn, for all n, and there exists an r bigger than 0 such that the absolute value of Pn is less than r for all n, then we have that Pn converges. All right, I don't want to go ahead and prove that. That's something straight out of analysis. It uses the least upper bound property of functions. I should also say, though, that this could hold if we exchange this around. So it could be monotonically increasing, monotonically decreasing. But the idea is that if your sequence is decreasing, but you know that there's a bound somewhere, then it's going to stop somewhere, either at that bound or above it if it's a decreasing sequence, and vice versa for the other way around. So, so then let's go ahead and talk about Heron's formula. So Heron's formula is this: it's xn plus 1 over 1/2 of, let's just find square root of 2. 2 over xn plus xn. Okay, so the first thing I'm going to show you is that this is actually a monotonically decreasing sequence, provided we start with xn being bigger than, say, square root of 2. So we'll let x0 be equal to 2, and so then we make sure we start above where we need to go. Okay, so then that tells us that the absolute value of xn plus 1 is equal to 1/2 of 2 over xn plus xn. But we know that okay, so now we're in a position where we can actually prove Heron's formula converges. So so let's go ahead and do that. So we'll just go ahead and call this a proposition. And so basically we're going to say let s be greater than 0, then setting x not is equal to s, and recursively setting x7 plus 1 is equal to 1/2 of xn plus s over xn. It follows that xn converges, or we'll just say the limit as n goes to infinity of xn is equal to the square root of s. All right, so let's go ahead and prove that. Okay, so first thing we should say is that square root of s is not equal to 0. And that is because we know that 0 squared is equal to 0, so that's what we have there. I'm saying that because I want to ensure that we have a lower bound that we can get at. And honestly, we might just cook up another lower bound as we go, but I just want to put that out first. It might actually be a useless line in the long run. But okay, so there's two things we're going to show. And all right, so first thing we're going to show is that xven is greater than the square root of s for all n. Okay, so we can show this by induction. So let's do this by induction. So first is get our base case. Well, x naught is equal to s, and that is indeed bigger than the square root of s. So check. All right, so then assume this holds for xn, and that will show it works for xn plus 1. All right, so we have that xn plus 1 is equal to 1/2 of xn plus s over xn. Okay, so now we're going to use the AMGM inequality. And so we're going to replace this average with lower bound of square root of a plus b. So this is an average, and so then we can replace this with the square root of xn times s over xn. Well, this gives me the square root of s. So done. And so thus, by induction, we have that xn is bigger than square root of s for all s, for all n. Okay, good. Now what's next? We can show that it is, so let's do next. Next, let's show that it is a monotonically decreasing sequence. So we have, if we take a look at xn plus 1, and again this is written as 1/2 of xn plus s over xn. Well, since xn is bigger than square root of s, this tells us that s over xn is less than square root of s. But the square root of s itself is less than xn. So thus we have that xn plus 1 is which is less than or equal to 1/2 of xn plus xn, and that is just xn. Okay, good. So now we have a sequence. So now we know that xn is monotonically decreasing and bounded below by square root of s. Okay, so now is where I'm going to actually start employing the continuous function stuff that we developed. So, one thing we should note is the function f of x equaling 1 over x is continuous and is continuous, let's say, away from 0. And in particular, it is continuous on the interval of square root of s to s, okay, which is where all of our xn's live. How do we know that? That is just the limit theorem that we had a little while ago, somewhere in here. Here. So here we just replace Pn with 1, and then that gives us 1 over Qn, and so then that would actually just tell us how those limits hold. So there we go. Okay, now if we take a look at xn, then what we get, or say xn plus 1, this is actually the same as 1/2 of 1 over, or sorry, of xn plus s over xn. And I'm going to write this, I'm going to write g of x is equal to 1/2 of x plus s over x. Now, since this is continuous, and the sum of two continuous functions ends up being continuous, g of x is continuous on the square root of s to s interval. Okay, so now what can we use? Well, we know that since xn is monotonically decreasing and bounded below, we can conclude that xn converges to a limit L in, say, in R. And specifically, since we know that lives in here, we can say better than R, we can say it converges somewhere in here. Okay. So, let's go ahead and do this. So basically, if I take limit on both sides, I get the limit of xn plus 1. That's going to be L. And if I take the limit of 1/2 of xn plus s over xn, this is the same as the limit. N goes to infinity. I should probably have that there. Of g of xn. And since g is a continuous function, this is the same as g of the limit of n goes to infinity of xn. And so this is g of L. Okay. So that tells me L satisfies this relation. L is equal to 1/2 of L plus S over L. Okay, now let's go ahead and solve it. This tells me then that I have, say, multiply both sides by 2, and so we get 2L, and subtract L, so we get L is equal to S over L. That tells me that L squared is equal to S, and that tells me that L is equal to plus or minus the square root of S. But this is a positive sequence, and bounded away from 0, in fact, and so, in fact, L is equal to square root of S, because since L has to live in this interval. And there you go. So we just proved that Heron's formula converges. There's another more finicky proof, which uses greatest lower bounds and greatest lower bounds and least upper bounds, straight out of real numbers and things like that. But I feel like this proof is a little bit more slick, and since we're not doing like proper analysis in this class because it's not a prerequisite for the class, I figure we can get away with talking about some continuous functions. Okay, cool. So before we wrap up, I want to talk about a couple more things, and these things, if we go back to the beginning, before we lose track of everything. So we've talked about metrics, we've talked about sequences, and finally I want to talk about series. And so let's go all the way back. There we go. And let's talk about series. I'm not going to spend a whole lot of time here. You spent a huge amount of time in Calculus 2 talking about series. But we should talk about it a bit here. So we're going to let Pn be a sequence in R. Then the series a series or the series associated with, say, Pn, is written formally as sum of n goes from, say, 1 to infinity of Pn. And we say that the series converges if we write, if we take the partial sums, the limit, as capital N goes to infinity of the sum of n equals 1 to n of Pn converges as a sequence. All right, and yeah. So that's the series for you. Probably not surprised at the definition. Probably the most important series that we're going to be talking about, and we even just threw it out there last time in the intro lecture, is the geometric series. And the geometric series basically says this. Let the absolute value of x be less than 1, then the geometric series sum of x to the n equals 1 to infinity converges. It diverges otherwise. We'll just go ahead and show that it converges. That's pretty easy. Let's see. All right, we'll take the partial sums. So consider the partial sums of sum n equals 1 to n of x to the n, and we'll call this S. It helps to visualize this a little bit just by writing these out. So it's going to be 1 plus x squared all the way up to x to the n power. And I'll call this Sn. And if you want to actually have a nice closed form for Sn, the slick thing to do is to take Sn and multiply it by x. So xSn is equal to x plus x squared plus x cubed plus all the way up to x to the n plus 1. Now if I take the difference of these two guys, it gives me something else. It tells me that Sn times 1 minus x is equal to 1 minus x to the n plus 1. Because basically this cancels this guy, this cancels this guy cancels this guy, all the way down, and it leaves 1 and n plus 1. Okay, so that tells me then that Sn is equal to 1 minus x to the n plus first power over 1 minus x. Now, since absolute value of x is less than 1, this means that x to the n plus 1 converges to 0 as n goes to infinity. Thus, we have the sum of n equals 1 to infinity of x to the n is equal to 1 over 1 minus x, and that's that. And that is convergent and finite. So done. Okay. One last thing we should probably talk about, and that is a harmonic series. And so let's go ahead and talk about the harmonic series. There's a bunch of ways to show that this diverges, and this is going to be somewhat instructive. The harmonic series is given as this. So the harmonic series is given as the sum n equals 1 to infinity, 1 over n. This series diverges. Okay, best way to do it is by picture. So let's take a look. All right, so if we take a look at 1, and so this is going to be here, height 1, and so this is 1 over 1. Here, then if we have 2, it's going to be, say, 1/2. And we look at 3, it's going to be, say, 1/3. Put a 4 here, and this is starting to get tedious. It's going to be 1/4, etc. So the idea is that all of these guys sit underneath this integral, and so if this is 1 over x. Well, actually, that isn't going to help us. We want to show it diverges. So I'm just going to shift it over a little bit, and instead we're going to talk about this curve. There we go. And this is 1 over x plus 1. And so kill that. And so what we're going to show is the area of this one diverges. So the partial sums, so consider the sum n equals 1 to capital N of 1 over n. Just visually, we see that this is going to be bigger than or equal to the integral from, say, 0 to capital N of 1 over x plus 1 dx. Okay, but we know what this is. This is going to be the natural log of x plus 1 minus the natural log of 1, which is 0. All right, so then, not x plus 1, it should be ln of n plus 1. All right, now if I take a limit as n goes to infinity, we know that the limit of ln of n plus 1 is equal to infinity. Thus, sum of 1 over n equals 1 to capital N, diverges. Okay, so this is sort of a calculus take on the divergence of the harmonic series. But it was first proven by Oresme back in the 14th century, it was 1300s sometime. And this is roughly around the same time that you see power series starting to show up in India. But yeah, Oresme was the first to demonstrate that the series diverged, and he obviously didn't use this method. Maybe I'll put a little homework assignment, the problem in the homework assignment to have you walk through it. A lot of you probably have seen this through calculus 2 already. But yeah, it's a fun little proof to know as a mathematician. And so one thing that we can say is that the power series, or not the power series, the p series, sum of 1 over x to the p converges, put n here, 1 over n to the p of n going from 1 to infinity converges when p is strictly bigger than 1. And this can be proved, again, using comparison tests with series, so same sort of deal. It diverges, the p series diverges for p less than 1. And this is a fun bit of analysis. N equals 1 to infinity, 1 over n squared is equal to pi squared over 6. And that was proven by I think it was, I want to say it was Euler. Well, let me double check. Yeah, it's called a Basel problem. And so, yep, it was solved by Euler. And I think it was solved by Euler in 1734. When was Euler born? He was born in 1707, so 1734 he would have been, what, like 27? Something like that. Yeah, so, yeah, that was a really big problem that I solved, and it was pretty clever the way he got about it. I'm not sure we have the space to talk about it, but yeah, might be fun to look at sometime. Okay, cool. So I think we'll end this lecture here, and yeah, we'll go back to the office.
Okay, so that's metrics. So a metric is basically a ruler that you can put on different spaces. It can be a collection of functions, and you can put a distance there. You can have any arbitrary set and have a distance. And there's a whole lot of different ways of talking about these things, but the things that we're going to be really caring about and the things we're going to really discuss more than anything is the Euclidean distance and the uniform distance on continuous functions. And that's going to be the core to everything that we do in the class. The Euclidean distance is going to come up whenever we talk about real valued quantities. So for instance, we are going to talk about the Euclidean distance between an integral and say its Riemann sum, and because both of those are real values, and so then we're going to basically try to quantify their distance in terms of the Euclidean metric. And then for polynomial approximation, we're going to use the uniform metric, and also probably also for Fourier series, although I think usually that's better in terms of the L2 norm, but we'll talk about that if we need to when it comes up. In any case, I hope you enjoyed the lecture, and hope everything's clear, and soon we'll get to proper numerical analysis using these concepts. All right, anyway, I'll see you next time.